Hi there, I'm Elaine and I'm going to talk to you about binary and hex to help you with your computing fundamentals. Let's go back to primary school where you learnt about decimal values. So decimal is represented using the hundreds, tens and units, or base 10. And base 10, each 10 goes up to the power of 0, followed by to the power of 1, followed by to the power of 2, and all the way up 3, 4, 5, etc. So 1000 is 10 to the power of 3. You can only use 10 possible values under each placement, so 0 to 9. So 0 would just make it 0 units, 9 units, and then the next value, if you wanted 10, would be a 0 and a 1. So that's base 10. Well, base 2 is the same. You can write it out exactly the same. You write in the first placement 2 to the power of 0, then 2 to the power of 1, then 2 to the power of 2. Well, instead of it being 1, 10 and hundreds, it's now 1, 2s and 4s. So representing the same value using the ASCII table, it's a byte used to represent, so 8 bits used to represent the data. So for example, the bell is represented as decimal 7, which is 7 units. But in terms of base 2, you only have 2 possible values that you can use, a 0 or a 1. So you have 1 1, you have 1 2, and you have 1 4. So added together that makes 7. So in binary it's 1 1 1, in decimal it's 0 0 7. I'm going to do a new slide and just explain this a little further. So going back to our hundreds, tens and units example, just to make sure that this is clear to you. So back into our hundreds, tens and units, and we have our 4s, 2s and 1s. So we can't call it anything else. So 4s, 2s and 1 units. In comparison, so this is base 2 and this is base 10. And here we have 0 to 9, and here we have 0 to 1. So if we wanted to store the values, say, my favourite number 42, we'd need no hundreds, we'd need 4 tens, and we need 2 units. We find this easy because we are used to operating with base 10. But if we wanted to store the number 42 here, well, we don't have enough, because even with all of these set, we still only have 7. So we would actually need to go a little bit further. So 1, 2, 4. So remember, this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6. So 2 3s, 2 times 2 times 2 is 8, and then that's 16, and that's 32, and that's 64. Alright, again, it's like our hundreds, tens and units, but it's not so easy because that base 10 is very easy for us to understand. Like thousands is next. If you want to represent 42 in binary, then you need one of these, 32, plus a 16, so that's 48. No 16. Sorry, plus an 8, so that's 32 plus 8 is 40. No 4s, 1, 2, and no 1s. And that equals 42. So base 2 and base 10 are represented in exactly the same way, with your 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, and in this case you've got your 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. So the same, except the number 2 instead of the number 10. And when it adds up, 10 to the power of 1 is 10, 10 to the power of 0 is 1, 10 to the power of 2 is 100, 10 to the power of 3 is 1000. So it's a lot easier for you to understand. Well, with the 2's, you've got 1, 2, 4, 8, 16, 32 and 64. So you have to, you start to learn these, you start to just know these numbers off by heart. So when you press the tab key, that's represented as a 9, so 9 units, and 2 times 2 times 2 is 8, so one of those and one of those. So in binary it's 1001, but in decimal it's 9. So represented as base 10, it's 9. Represented as base 2 binary, it's 1001. So with the decimal again, base 10 compared with octal. So this is another example, but instead of using binary, I'm giving you a quick look at octal. So octal is where you have base 8. So with base 8, you've got 0 to 7. With base 10, you have 0 to 9. So is it obviously including the 0, you've got 8 possible digits. So 8 to the 0, 8 to the 1, 8 to the 2, 8 to the 3 goes up in 8s this time. And the letter H in decimal is 72, and in octal it's 110 as shown. So the same principles apply here. So you have other representations as well, but let's go back to our binary. Just sort of throw that one in there. So to convert into zeros and ones, base 2, the ASCII value hello, you find what H is. Capital H is 72, and that is a 64 plus an 8, which is 72, and everything else is 0. Again, like your hundreds, tens and units, you just put the values underneath the placement. E is, where's our E? 101 decimal, so that's a 64 plus a 32, which is 96, and a 4, which is 102. And L, we go to our L here, 108, and we need a 64, a 32, which is 96, plus an 8, 104, plus another 4 to make you 108. And so the further one would be, it would be exactly the same. And a 0, an O, little o, lowercase o, is 111. So that's no 128, that's too big. 64, 96, what did I say? An O is 111. So we've got 96. Now, if we added on a 16, that would be too much. So we can't have a 16. So we've got 96, we've got an 8, which is 104, 108, 110, 111. That gives us an O. So 0, 1, 1, 0, 1, 1, 1, 1 gives us our 111. So that's hello. So here's another example that we can try where we're going to convert all of these binary values using the ASCII table into their equivalent letters to find a little message in there or a word. So have a go at that now. I'm going to do the first 3 to get you started. So the first one is, let me just find my pen. The first one is 64 plus 16, which is 80, 84, 86, 87. Correct me if I'm wrong. That's a W. So capital W. And the next one, 64 plus 32 is 96. Plus 4 is 100 and a 1. 101. So we go down here and we find it an E. Let's choose an E there. I just fancy using blue. And the next one, 64 plus 32, 96 plus 8, 104, 108, 108. So we need 108, which is an L. And this, in this case, let's add them up, 64, 96, 98, 99. So what's 99? It's a C. Okay, and what's the next one? Does that look familiar? So the next one is 96 plus 4, 104, 108, 109, 111. So what's 111? It's our 0. And the next one, 96 plus 100 plus 8 is 104, 108, 109. So what's 109? M. You see it's going right now because I think I must have changed the top with a copy and paste by accident. And then this one here is the same as this one. But obviously the computer would need to add that up again because it doesn't know that. It's just that I do. All right, so that says welcome now that we've done it right. So hopefully you can see how that came about by translating the values into binary. So each of these letters would go across the computer, would go across the network or onto the computer to be processed as these binary digits here. All right, now this is a bit messy, so let me just delete this slide here because I don't want it. And let's look at this. So how we work these things out. Let me just remind you. So underneath here we have 2 to the power of 0, 1, 2, 3, 4, 5, 6, 7, and on it goes. And what you need to do is work out the number. So in this case, let's take 181, and we can work out what we need for 181. So we're likely to need one of these plus one of these. Now what do they add up to? 192. That's not right, so we don't need that. So we need 128 plus a 32, which is 160, plus 16, which is 176, plus an 8, I imagine, 176. No, that's too much, so we don't need that. So we're on 176, a 4, that will take us to 180. We don't need a 2, we just need a 1. So that would be the binary representation. It's not easy being a computer, it does it a lot quicker. So that's how you work out this one here. So if we wanted to work out how to represent this one, say 142, let's just do another one. We would have a 128 for sure. We wouldn't have a 64, that would take it beyond what we need. So we're looking for 142 in this case. We've got a 128, so all we need now is 14. So that's no use to us, that's no use to us. We'll need an 8, and then we need something to make it up to 14, which are those. So 8 plus 4 plus 2 is 14. So 128, 136, 140, 142. Again, that's what the computer has to do very, very quickly. So more. Gosh, it doesn't stop, does it? So an IP address is represented in this way. Lots of things are represented in binary. So 192 would be one of these. 128 plus 164, what's that? Happens to be 192. If I've got my sums right. It's going to be a 128, and then we need 40. So that's no good, but that is no good. Yes, 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 yes. You get quite quick at these, especially when these are written down, and you start to know them in your mind as well. A 10, well, we don't want one of those, or one of those, or one of those, but we do need an 8. We don't need a 4. We do need a 2, and there we have it. And again, a 12, we'll have an 8 set, and we'll have a 4 set because they add up to 12. So that's our IP address stored as binary. So let's look at Unix file permissions. They're also can be set using binary. What you'll find is, well, when we've looked at permissions earlier on, let me just go and log on to my Ubuntu and I can show you this. Okay, so we're looking here and I'll show you the permissions. You can see they're set in little blocks, RW, RW, -RW. So that can be X as well on the end. So I'll show you back a directory. ls-l to give me a listing of the directory. So you can see RWX, RWX, R something X. And you can use binary to set the permissions for these blocks. So 124, 124, 124, which is to represent the 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. And as you only have 3 digits, so the first digit is for execute, the next one would be for representing write, and the next one would be to represent R. So if that was set, you would have, so if that was set to 1, for example, or we can do that. If that was set to 1 and that was 0, 0, then that would be read, just read. In this case here, we need to set that as read write, so we'd need that one set, and that one not set, and the same for here, that one, and that one. So this would be our read, our write, and our execute. Read, write, and execute. This is where we're using binary to actually represent permissions. So the command for that would be, I can't do it there, chmod, change modification, 4 plus 2, so that's 6, 6, and then 4. Hopefully that made sense. So 6, 4, 4 would go in there. The next one, let's just do the next one. We have read, write, execute. So that's the read, the write, and the execute set, but read and execute only set. And it looks like nothing's set. The hyphen's gone there. So 0 permission for everybody else. So that's owner, group, and the world for this one. In this case, it would be a 7, 4 plus 2 plus 1. So 7, 4 plus 1, 5, and 0. So the command for that would be chmod 750 typed in at the command line. So hopefully that makes sense. So they're in blocks of 3 to set the permissions for the owner or the user, the group, and everybody else. I can quickly show you that now. So let's give you an example. I'll just go into this workspace, cd hello world. Let me just show you that file, the permissions there. So chmod 660 will take away the read for the world, as you can see. 600 will just give me read and write, as you can see. So you can use binary quite easily, and I'll put 660 back, and you will see that's how you can set the permissions using binary. So very useful little tool there. Oops. Right, back to the slides. And the next thing I'm going to do is cover the last base. So I touched very rapidly on Octal, but base 16 is actually used. So again, you've got your base 10, you've got your base 2, you've got your base 8, and now you've got your base 16. You often see this in association with color codes. Let's have a look. So you'll often see #FF. What does that mean? Well, again, let's compare it with our base 10. With base 10, you've got 10 digits, 0 to 9. With base 16, you've got 0 to 15. Well, how do you represent them? You say 0 to 9, which we know about, and then we've got A, B, C, D, E, F. Well, this is your 10, B is 11, C is 12, 13, 14, and F is 15. 0 to 15 can be represented using base 16. 0 to 9 could be represented using base 10. So again, same thing. 10 to the power of 0, 1, 2. 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. And in this case, you've got 16, 0, 16, 1, 16, 2. So 116, or you've got all the way from 0 to F, that could go in here to represent how many of them you want. So how many 16s do you want? Well, I want 12 of them. C means 12 of them. Here it's saying I want 4 10s. I want 4 units and 2 10s to make 24. Here I'm saying I want 12 lots of 16. Here I'm saying I want, 12 lots of units and 7 lots of 16. Do apologise if I make a few mistakes like this. So this is saying I want 12 units. That put me off, didn't it? Yeah, so don't let that put you off. That means units. 16 to the power of 0 units. So I want 12. So there's the 12. And I want 7 lots of 16. Okay, so 7 times 16 plus 12 is what you will get to make this value here. 7c is 124. Okay, and so that's used to represent colour. So for example, hex pairs are often used to represent your RGB. So you have the possibility of a pair of FFs, which is 255, to represent, so 0 to 255, to represent 256 possible combinations in every R, G and B. So 255 here will allow you full red. Nothing here will allow you no green, no blue. So that's pure red. Pure red represented using all the possible values. If this was 128, then that would be a lighter red. Okay, if it was 0, then it would be no red. So you've got between 0 and 255 to represent your variations of red, the red colour. So the reason you would use hex rather than binary is because you have more possible choices for your colour. So you have 255 without using as many digits. Okay, and here's another example here. So we would represent red, green and blue for pure yellow. So 255 would be F, 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 F and 0, 0. And in the case of 192, how would we use this? How would we represent 192? So how many 16s would we need to represent this colour? Well, let's work it out. Okay, so 192, we need to work out what 192 is. Don't have a lot of space here. How many 16s do you need to make 192? So is it, let's just guess. If I was the computer, I'd know because I'd be really clever. But is it 10? That's 160, so it's not that. Is it 11? That's 176, so that's no good. Is it 12? What's 12 times 16? So 160 plus 32, so that's correct, isn't it? So it's 16. So sorry, 12. We need 12. Now we have 0 to 9, A, B, C. So this is 10. Whoops, 10, 11, 12. So the answer is C0, because we don't need any units. C0 would make silver in the case of silver. How do we make purple? Okay, well, let's start with how many 16s do we need to make 128? Again, if I was the computer, I would do this a lot quicker. But I know I don't need 10. So is it something like 8? So 16 times something will make 128. And if you've got an excellent maths brain, you would work this out straight away. So is it 8? Let's have a look. 8 times 16. So 4 16s. 64. Twice that is 128. So that to me is an 8 and no units. So 80, nothing in terms of green, and 80 in terms of blue. So 80 lots of red, 80 lots of blue in terms of hex, and no lots of green to make your purple. Hopefully that makes sense. It's a case of thinking in the right base, and obviously just going up by the zeros and the power of 1 and so on and so forth. But in hex, it's just remembering what base it is and remembering that you have the additional letters to represent the numbers 10, 11, 12, 13, 14 and 15. So that's hex. So let's go back and summarize. So we've covered some binary, we've covered some hex, and let's do a quick summary of all of those. New slide. A quick summary then. So we have binary, which is base 2, and that's our binary. And we have a possibility of 0 and 1 as our digits. So only 2 digits because we're binary. We have base 8, which is octal. Don't see that used very much. We have 0 to 7 possible digits, which is 8 digits. We have our base 10, which we all know is our decimal, and that gives us 0 to 9 digits. So that's 10 digits. And we have base 16, which is our hexadecimal, and that is where we have 0 to 9, A, B, C, D, E and F. 16. So we've got 16 digits, and all of them go up by the base to the power of 1, the base, 0, 1, 2, 3, 4, etc. So substitute that with your 2 or your 10 or your 16, and you will have the correct values that you need. Hopefully that's given you a nice overview of decimal, octal, well, a little bit of octal, binary and hexadecimal. And good luck experimenting. The best way to learn this is just to keep practicing, keep answering questions like these, having a little look at what the data might look like on the system, playing around with different calculations, like how does an IP address look, setting security permissions on Unix, and hopefully you will understand how it all works, and it'll just come to you eventually. You'll know the numbers without having to think.